Thank you for having me. This is a picture of me with our mascot, Blinka. It's a giant puppet, which is always fun to take pictures with. You may say, why am I taking pictures with a puppet? I'm Scott Shawcroft. I go by Tan Newt online. I'm a freelance software engineer. I work from home in Ballard, which means I have no excuse for not having come here before. But I plan on coming again, so thank you for having me. I'm the lead for CircuitPython. And CircuitPython is Python that you can run on inexpensive computers that are like a couple dollars a piece. There's no operating system, so we don't participate in the Linux versus Mac versus Windows debate. We don't use any of them. And we'll go into more details about that a little bit later. Here's the plan. I'm going to do the live demo at the start because, get it out of the way, get you all excited about Game Boys. And then what we're going to do is we're going to do a vertical slice of how the demo works. So we're going to start at the very highest level of what is CircuitPython? You mean you don't have an operating system and you have kilobytes of RAM? What is that? And then we'll go all the way down to the wire and we'll talk about what the cartridge wires actually carry and how we make a sound play. So let's do the demo. And Catherine is going to be awesome and help me. So we have a Game Boy here. This is a DMG. It's green. My boss has got me the green one. And so if you can hold that, let's hold that here. So we're just going to make some noise. So let's turn it on. Wait, what? So the first two notes you heard are the Game Boy's starting up, and that's something you can't change. But it played a third note, and the third note is what's interesting. So what we have inside of here is a Game Boy cart that I designed, and it's running Python. It's running CircuitPython. So if we plug it in, it's not USB-C. Okay, so now if we pull up Finder, we should get a CircuitPy drive. Take my word for it, it might be a little small. And there's this file called code.py. This is the file that is run automatically by CircuitPython when it starts up. All in that single thing. Oh yeah, it's going to make lots of noise. So what happens is that every time I save the file, and it doesn't crash hopefully, it will play the note. So I just hit Command S to save, and now play the note again. And what I've also have documented here is we can tweak the bits that are at that very lowest level that dictate what the sound sounds like. So if I hit, I uncommented that, and now the note is lower. The point being is that CircuitPython makes it really quick and easy to iterate on your code in a hardware device like this. Well, let's have some more fun with sound before we get into slides of code. Let's play with this. It made the note longer. That's the envelope register. A register is, you can think of it as a hardware API. It's literally bits that mean something to a custom piece of hardware. And in this case, it's the hardware that makes noise on the Game Boy. The most fun one is the sweep register. And what this does is it changes the pitch over the duration of the note. And you might recognize this as the way that they do lots of sound effects. Oh, I made it really, really short. So let's increase the duration, or the time, I think. I was playing around with this earlier. Whoa. A little bit longer. I'm trying to make it as long as I can. There we go. That sounds really familiar, right? But what if you're going down a warp pipe? Or you just died, one of the two, right? Sound familiar for sound effects, right? Well, I'm going to do one more to leave us on an uplifting note. And that's the demo. I'm going to eject because you got to keep your drives happy. And I'm going to save my battery. 4 AA's will last quite a while though. And let's get started. So we did the demo, and you might be saying, how does that work? You have a Game Boy cart. That's what we're going to talk about. And the highest level that we're going to start with is just CircuitPython. What is CircuitPython? So CircuitPython is running in the cartridge itself. And let me just, Right, so this is how big a computer running CircuitPython is. If I plug this into power, like if I turn the Game Boy on without it, it will still work. Nothing on my computer was doing anything except changing the code. That's the high level what CircuitPython is. We tend to think of it in 2 parts. We think of it as code, and we think of it as community. Because we're an open source project, and there's more to it than just the code that runs those things. There's everything around it, and I call that the community. Let's go into a little bit more detail. All of you are here because you know Python is great. Python is great because it's fast to get things done in, and that is still true when you bring Python to hardware. As I said, CircuitPython, the code and the tool chain lives on the device itself. So if you wanted to try playing around with the bits to make sound, like I could just give you the Game Boy and a USB cable, and you'd be off and away. You don't have to download anything. You'll probably have text editors. That's the only thing you'd probably want. If you want to see the actual code that's running it, we are all open source, MIT licensed, so you can go to the URL there. And credit where credit is due, we're built on a project called microPython. They laid the foundation for this idea of taking a small, inexpensive computer. They can run like 48 megahertz, 120 megahertz if you're lucky, maybe 600. Whew, I don't know what we do with 600 megahertz. And like kilobytes of RAM, and it makes it feel like Python. So MicroPython did a lot of that work, and thanks to them. On the community side, we've taken a deliberate approach to our community. We want to build it as an inclusive way. We have a code of conduct. It was originally a contributor covenant, but we've kind of done one rev on top of that. And we enforce it. So we're welcoming community in that way. We have an active community both on our GitHub and our Discord server. And I'll have the link to the Discord later on in the talk. The community also involves all of the Python stuff that makes things easy to use. Those are our libraries. And we have over 170 of them currently. Those aren't the things that you would think of as standard library with Python. Those are the things to make this sensor work or that sensor work generally. And we have 60 plus supported boards. So these are some of the form factors of devices that you can buy online that run CircuitPython and can run your code. The Trinket M0 is probably the smallest one, and we have everything in between. We have Game Boy cart, although you can't really buy that yet. I do have a lunchbox full of stuff, so after the talk, I'm going to hang out and answer questions and show off hardware if you're curious about that. So, Game Boys. I promised you we would talk about Game Boys, and luckily for you, that's all we're talking about for the rest of the time. There are 3 main types of Game Boys in that kind of first generation. The DMG is on the left, the gray one. That's exactly what, the green one here is also that generation. It came out in 1989, just had its 30th birthday. The one in the middle is a Game Boy Pocket. This is a revision of it that made it a lot smaller and lighter. It's actually the first one I had. And then on the right we had Game Boy Color, which is very similar to the Game Boy Pocket, except that it had color. None of these have lights. I gave my niece one to play it, and she called me over. She's like, how do I turn the brightness up? You gotta angle it right. It's all about the angle. Or if you have one of those worm lights that like shines the light on top of it. I did bring one. I have one of those if that's your trigger nostalgia for you. Let's talk about the guts. So I took the tops off. You can see the difference in complexity. The DMG on the left, the original, has more circuit boards in it, which makes it more interesting. The right two are a single circuit board, which simplifies the assembly a lot, and they're a lot more similar. The things I want to point out here are, you can kind of see it, the big black chip in the middle is labeled CPU, that's the CPU. And that includes also the sound generation hardware. So it has basically everything in that chip. The other chips are just your RAM, not that interesting. And then the big black piece of plastic there is the cartridge connector. So right, you have a game, slide it in, and turn it on, and you can play your game. That's how code is stored, right? Like, there isn't any actual code on this piece of the Game Boy, it's all on your cartridge. What does a cartridge look like? Here's a couple. Tetris is kind of the most basic, where it's literally just a piece of ROM. It's memory that you can't change at all. And the way that it works is, in the cartridge pins, you get an address that say, read me this piece of data. And then on 8 lines out, you get the data back. The middle one, Mary Kate and Ashley's pocket planner. As you can see, I cut cartridges open to make them fit my cartridge, and so I go to the game store and get the cheapest Game Boy games I can, and this is one of them. But the card itself is actually pretty interesting for a couple of reasons. One, it keeps track of time, which is the crystal in the top left. It's taped down by a piece of tape. It has more memory, so the chip below that is actually allowing it to swap different memory regions in. And then it also has save state. Right? You play Zelda, and you've gotten to a particular level, and you have a sword. How do you actually save that? Well, SD cards and the technology behind them didn't exist at this point. What they did is they just put a battery in it, and then it's RAM. The thing on the top right, the circular thing, is a battery that fits in the cartridge. If you've held on to your games because you want your saves to exist in the last 30 years, I highly recommend you look up how to swap that battery out. Otherwise, you may lose your saves. There are also ways of just downloading them now, too. And then the cart on the right is the cart that I designed, and we'll go into the way that that works. Basically, we have a microcontroller in the middle there that is pretending to be memory. Give me the data at this address, and we say, oh, I'll have this data. We don't really care. And we'll go into more details about that, but basically, at a 1 megahertz rate, we have to give it data to do something. It's not too bad. The microcontroller on here is 120 megahertz, so theoretically, we have 120 instructions to do something in between. So, this is what the demo was when we started. This is the basics of it. I took out all the bits that made the funny sounds, and left this bottom bit, which is the one that plays the sound. And I said it was setting a register. And this is kind of how registers are documented. And the one we care about is at the address FF14. This is the API for the sound hardware of a Game Boy. This is one piece of it. So this Game Boy CPU can write to that address 8 bits. And these 5 of the 8 bits mean something, and this is what those mean. The 8th bit is high, the sound will start. Pretty simple, right? So how do we set that 1 bit from Python? That's where we're going. Here's the overview. I was telling somebody earlier, I was adding a lot of not Python to this talk, so buckle up. There's no OS here, though, so we can cover every layer, which is really neat. At the highest level, we have pure Python, which if you're comfortable with Python and want to contribute, you can totally just live there. Its goal is to make it easy to use, and then rely on the lower level Python APIs that are actually C. So that's kind of this second and third bullet point is, I want to trigger some C code to work, and here are the Python APIs that I'm making available to do it. The third bullet point is all about that hop from Python land into C land, maybe checking your arguments so they're what you expect, and then converting them to C types. Below that, we have this lowest level of C, which is like, for the specific chip that I'm doing, I want to set these 8 pins to these different ones and zeros. This is how I do it on this chip. And then I told you we were doing hardware. We're actually going to talk a little bit about what happens on the wires itself to make this happen. So stick with me. Okay, this is our demo code. This is what we were talking about earlier. The part that we're going to focus on is this very last line, which is just an assign, right? Imagine that GB is just one big array, right? That's the mental model that we're going for. And we set offset to FF10 before, we're adding 4, and now we're talking to FF14, which is the register that plays a tone. You may not have seen it before, but we have this special binary syntax that Python uses. You can do 0B and then 1s and 0s to actually see a binary representation of a number. You may have done it with hex with it where it's 0x. And in hex, this value is hex 87. What's below that? You may ask, hopefully. Here's our implementation of set item. What we're doing is we're saying if the address, the index that you're going for, is above FF00, this is where all the special stuff is. We have a special instruction that we can use to load data into there. And we have a sequence of bytes that we have to transmit in order to set that memory. And what we're doing is we're patching that sequence to include the address that we're actually going for and the value that we want to save there. And then we're calling this, so there's the sequence, and you can see that there's holes at 2 and 4. We're filling those in. And then we're calling Q commands. This is saying, hey, next time the Game Boy wants something from us, queue up these bytes that are going to do this for us. It's going to load it in, and it's going to play a tone. How does that work? Well, GBIO is a C module. So this is where the embedded hacker side comes in, who's willing to drop into C to interface with the hardware directly. What you'll find is that I think both CPython and CircuitPython are generally dictionaries all the way down, literally. In CircuitPython, we use structs a lot to represent Python objects. You can think of a struct as just a designation for a set of values in a particular order. Here we're saying we're going to have this GBIO module available in Python. We're going to say what type it is, and we're going to just give you a link to the table of names in that. Those are the globals. So this is the table. It's just mapping strings that you can use in Python to the objects that you're referencing under those names. That's a dictionary, essentially. It's a dumb way to store a dictionary, but it's a dictionary nonetheless. And there is Q commands. That's the thing that we called from our Python. And it's pointing us to an object in memory, in the microcontroller's memory, that it's going to call. That function has this fancy syntax to say, like, oh, make an object that, like, from Python you can know is a function. And then it's going to call this custom C function, which is documented in RST. So from our read the docs, you could see that as what a normal Python argument would look like. Like, you don't have to worry about the fact that it's C. We do this portion of the implementation worries about translating it from your Python world to its C world. So it takes your objects in, and it makes sure that, like, you're giving it what it actually wants, right? So in the way that when you're doing Python, you make sure it has something, right? This is kind of duck typing of, like, let's make sure it is actually an int at this point, because we do actually need it as an int. And then you can see that if it doesn't match our expectations, we're able to raise a value error. So you would see, like in Maria's talk, a stack trace that says, oh, by the way, like, the instruction buffer must be a byte array. That is where you would see in a stack trace. And this now that we've passed all of our argument validation and we've converted things over, Now we're going to jump into the very chip-specific C code that we kind of dubbed common HAL. And this is the file location. You can see it's for a particular microcontroller, the same D. And we have the same function call here. Now I want to talk about DMA. Anybody know what DMA is? A few people? So, okay, this is really cool. DMA is for direct memory access. What it does is it's something that helps the CPU. Imagine that you have a WAV file, and it's, thousands and thousands of bytes long. And if the CPU is responsible for copying that from here to here, you'd use a lot of CPU cycles to do it. What DMA allows you to do, and what we're doing here, is saying, like, look, we have this thing, and we want it to copy over here at some pace. But once I tell you that I want that to happen, just do it. Don't worry about the CPU doing it. The CPU doesn't need to worry about it. What we'll set up is we'll just say, from this address in memory, just copy it straight to here. And the straight to here, you can see the DST address. That is literally the API for setting a pin's value for this particular chip. So there's 8 bits somewhere in the memory space of this microcontroller that when you set it to 1, you get a high signal on the pin that it's associated with. And so this is just having the direct memory access controller automatically do that for you. It's also great for playing back audio, if you're wanting to play back audio, where audio really is just a bunch of numbers at a certain frequency that change the position of like a speaker cone. It's mind-boggling how fast it can work, but it's super cool. All right, congratulations. You're done with the software side. Who's comfortable in hardware? Because we're going there. Let's talk about the wire. So this is my Game Boy cart. This is the same picture. I just turned it to make it easier to read. And what I want to point out is the things on the left that are gold colored are actually gold. When you insert your cartridge into the Game Boy, little springs will sit on every one of those pads to make electrical connection. That's how your Game Boy CPU talks to your Game Boy cart. So those are your wires. The wires I want to point out here are clock, the second one down, CLK. That's going to make sure that the cart and the Game Boy are kind of synchronized on when they're reading data and when data is maybe not so good. We have 16 address lines, so A0 through A15 are all address. And those are called a bus. So when you have multiple wires that kind of work in tandem, that's called a bus. So I'll just call it an address bus. And that address bus carries a 16-bit value over 16 wires. And then right below that we have D0 through D7. So that's our data bus. That carries 8 bits of data. Right? The other ones are kind of important, but we can skip them. Hardware people like to use things called timing diagrams to explain a protocol and how it works over time. So your horizontal axis, which I forgot to label, is time. The units doesn't really matter, although what you can think of as your units is the actual clock at the top. So traditionally you say when you have a falling edge, so when it goes from high to low, that's when something is valid, and then from low to high, something is valid again. And on the Game Boy, that cycle from rising edge to another rising edge is a megahertz, which means it happens 1,000 times a second, which ends up being like, what, 100 nanoseconds or something? It's really fast. Did I say 1,000? 1,000,000 times a second. It's a lot. It's a lot. And it just gets faster, which is even more complicated. So this is how the Game Boy CPU reads data from a cart. So we can see the address line here. The value changes when you see that X, that's when the value is being set, right before the falling edge. So the protocol is, the API is, the address will be valid on the falling edge of the clock, and then the cart has until the rising edge or so to set the data bus, which is the bottom thing, to a value that then the Game Boy CPU will read and do something with. Blow your minds? Are you on board? And the data bus is interesting also because that data can either come from the CPU or from the cart itself, which is why when the data is not being transmitted, it's in the middle, because it means anybody can do it. Okay. How do we get our 1 bit to play sound from the cart to the Game Boy CPU so that it can set that bit? This is the first step. We're going to take the value that we want to write, our 87, and we're going to use the 0E instruction, which is loading it into one of the CPU's small memory registers. Register A is what it's called. I did not come up with it. The second step is we're going to load the 14 piece of our address into another register, register C. And then finally, we're going to say, hey, look, that data you put in A, can you put it at FF plus 00 plus C? Save it there for us. And that's the thing that triggers the sound. That's the moment that 1 goes from the CPU to the sound hardware that's like, all right, we're going to play this sound. And you can see after that fact, it goes hatched because that cycle is being used by something that the cart is not doing. So from the cart's perspective, it's a break, it's a pause. And that is what our sound played. That's how we got sound and play. After that pause, we continue on and we keep running. I'm not going to talk about any more of that. So if you made it this far, good job. You've successfully gone from the highest level of CircuitPython all the way down to the very bottom wire. Congratulations. If you really liked that, and even if you didn't, you should watch this talk. It's an hour-long talk about all the different registers and all the different bits on a Game Boy. So if you want to know exactly like how to get the notes to play the exact thing you want or how pixels show up on the screen, this talk will cover all of that. What I've just given you are the tools to set those bits to do the things. Everybody get a picture? Awesome. If you want to live in CircuitPython land at the very top, we'd love to have you. Here's our Discord link. It's adafru.it/discord. Find me there. I go by Tan Newt. I'm happy to answer questions. We can use Python experience to make our libraries more Pythonic. We have a lot of folks coming from C-land, and they don't always use the nice things in Python that we know and love. So eyeballs on all of our Python code is always welcome. And here's my contact info. If you have questions after the fact, feel free to reach out to me. And I will leave it up there because people are taking pictures. Otherwise, thank you for having me. I'm going to hang out. I have a lunchbox full of different hardware things with a cute robot on it. If you want to see the lunchbox, it'll be up here too. Otherwise, that's it. Thanks for having me.